Assalamu alaikum students. This is lecture 21 of data structures and algorithms. The topic of this lecture is trees. We use chapter 13 of book 1. In the last lecture, we implemented a class for the binary tree data structure. We implemented functions to add and remove nodes from a binary tree. We implemented codes to calculate height and count nodes and leaves of a binary tree. We implemented codes to determine the type of a binary tree. We examined all codes for time and space complexities. We are still working with the same class definition. We are going to look at other functions in the class B tree. Now, the next function that I am going to talk about is a function that tells us whether the given tree is almost complete or not. So before that, let us recall what an almost complete binary tree is. There are three kinds of almost complete binary trees. If the tree is a PBT, then the tree is an ACBT. If the difference in height of the two subtrees of the root is 0, the left subtree is a PBT and the right subtree is an almost complete binary tree, then the tree is an almost complete binary tree. If the difference in height of the two subtrees of the root is 1, the right subtree is a perfect binary tree and the left subtree is an ACBT, then the tree is an ACBT. Have a look at the code. The function is given a node pointer self. First, the function checks if the tree pointed to by self is perfect, and if this is the case, it returns true. So this means that if you give this code a tree with 0 nodes, this will return true. If you give this code a tree with 1 node, this will return true. So if the first if condition is not met, this is guarantee that the tree that you have given has more than 1 nodes or at least 2 nodes. Correct? Now you have a tree with at least 2 nodes because the first if condition is not met. Come to the second if. Is there a left child? If the left child is not present and you have 2 nodes, this means that you have a root and you have a right child, but you have no left child. So this is not almost complete. So you return false. But if this condition is not met, this means there is a left child. And if a left child exists, we call the height function. This gives us height of the left subtree. And we place this height of the left subtree in HL. Now, if there is no right child and the height of the left subtree is 1, height of the left subtree being 1 means there is a leaf on the left and there is no right child. Repaint the tree in your mind. There is a root, it has a leaf on the left but no right child. So we return true because this is almost complete. But if the inner nested if is not met, then this means that on the left you have a left subtree of more than 1 levels and there is no right subtree. There is a root, there is a left subtree of more than 1 levels, but there is no right subtree. This is not almost complete, so you return false. If a right child is present, we call the height function again. And The height function returns us height of the right subtree, which we place in HR. So at this point, we have height of the left subtree, height of the right subtree. Now we check for the other two types of almost complete binary trees. If the height of the left subtree is equal to the height of the right subtree and the left subtree is perfect, then everything depends on the right subtree. If the right subtree is almost complete, then this tree is almost complete. If the height of the left subtree is greater than the height of the right subtree by 1 and the right subtree is perfect, then everything depends on the left subtree. If the left subtree is almost complete, this tree is almost complete. If the last two if statements are not met, then clearly the given tree is not almost complete and we return false. We now move towards tracing of this algorithm over this tree. When we start, self points to A. The first thing we do is check if this tree is perfect. Not perfect. So then we check if A has a left child. And it does. So the second if is not met. Then we call the height function for height of the left subtree rooted at B. So HL is 3. Then we check if there is a right child and it is there. So the if condition after HL is not met. And we call the height function for the right subtree. And we get HR equal to 2 because there are two levels of the tree rooted at C. Now, look at the second last if. Is HL equal to HR? No. Look at the last if. Is HL equal to HR plus 1? Yes. Now, check whether the right subtree rooted at C is perfect. And it is perfect. So the conditions of the last if are met. Go inside the body of the if. You are supposed to return a value, but first you are supposed to recursively call the is almost complete function and you will pass to it pointer to the left child of A. So when the function restarts, self is at B. Start from the first line of code. Check if the tree rooted at B is perfect. It is not perfect. So the first if is not met. Does B lack a left child? No. The second if is not met. Then we call the height function, which gives us height of the left subtree of B. HL is 1. Does B lack a right child? No. So we call the height function for the height of the right subtree of B and we get 2. Now come to the second last if. Is HL equal to HR? No. Conditions of the second last if not met. Come to the last if. Is HL equal to HR plus 1? No. So the last if is also not met. So we come to the very last line and we return false. Now that we have returned false to A, this answer is coming to A from its left subtree, and whatever answer A receives, it is just going to forward that answer or return that answer to the calling program. So A returns F, which is the correct response because this tree is not almost complete. It is not filled in such a way that no gaps are present. You can see that the node containing D does not have any children. So there are two gaps and then there is H. And this tree is not almost complete. Let us do another trace. For this tree, when we start, self points to A. First you check whether A is perfect. No, the tree rooted at A is not perfect. Then you check if A does not have a left child, but it does. So you compute the height of the left subtree, which is 3. Then you check if A lacks a right child. No. So you compute the height of the right subtree, which is 2. Now, is HL equal to HR? No. Is HL equal to HR plus 1? Yes. Is the right subtree of A perfect? Yes, it is perfect. Both conditions of the last if are met. Now everything depends on the left subtree of A rooted at B. If that is almost complete, then this whole tree is almost complete. So we recall this function passing to it pointer to the node containing B, and self now points to B. Start from the first line of code. Is the tree rooted at B perfect? Not perfect. Does B lack a left child? No. Find the height of the left subtree. 2. Does B lack a right child? No. Then find the height of the right subtree, which is 1. Is HL equal to HR? No. So the first condition of the second last if not met. Is HL equal to HR plus 1? Yes. Now find out if the right child of B is perfect. Yes, it is. Both conditions of the last if are met. Now everything depends on the left subtree of B. If that is almost complete, then the tree rooted at B is almost complete. So we recall the function is almost complete, passing to it pointer to the node D. Self points to D now. So we again check if the tree rooted at D is perfect. Not perfect. Does D lack a left child? No. Find the height of the left subtree. This is 1. Does D lack a right child? Yes. Move into the third if. Is HL equal to 1? Yes. Then you return true. So D returns true to B. Whatever answer B gets, it forwards it to the function that called this function. So B returns true to A. And A forwards this value to the function that called it. So A hands over true to us, which is the correct response. If you look at this tree, this is almost complete. Every slot is filled up to H. There are no gaps in the nodes of this tree. Here are two things that I want you to do. Draw a binary tree of height 4 in which only one node, which is the rightmost node in the last level, is absent. All levels are filled. In the last level, the last node is missing. Run the code for this tree. Draw a binary tree of height 4 in which the first 3 levels are completely filled and only 3 nodes, the leftmost nodes, are present in the last level. The first 3 nodes of the last level are there. Other than them, the last level is empty. Run the code for this tree. Now we are going to do time analysis of the is almost complete function. The worst case happens when the given tree is in fact ACBT. If the tree is not ACBT, this may be detected early with fewer function instances. The maximum number of function instances are called when the given tree is an ACBT. If the ACBT is of height h, h minus 1 function instances are called, 1 for each level except the last level. So the number of function instances called is OH. I want to express h as a function of the number of nodes. I cannot express the height of an ACBT as a function of the number of nodes n, but I can express the height of a PBT as a function of the number of nodes n. Let us recall, height of a PBT of n nodes is log of n plus 1. Which tree will have more nodes? An ACBT of height h or a PBT of height h? Obviously, the PBT will have more nodes. So I can say that the number of nodes in the PBT will always be greater than or equal to the number of nodes in an ACBT. In other words, I can say that the number of nodes in the PBT is an upper bound on the number of nodes in the ACBT of the same height. Height of an ACBT of n nodes is O log n. Time complexity of is perfect is On, and time complexity of height is On. When a single function instance is called, it calls these two functions, is perfect and height. Both of these functions have time complexity On. Sometimes it does not call these functions, then the function instance will take constant time. In the worst case, a single function instance takes On time. A single function instance takes On time and O log n function instances are called. So the time of the is almost complete recursion is O n log n. Now I proceed towards the space analysis. The function uses two variables, HL and HR, and the runtime stack Now the two variables are constant in number, but the size of the runtime stack varies. The worst case happens when the tree which is given to us is an ACBT. Then the maximum number of function instances are called. If the ACBT is of height h, h minus 1 function instances are called, one for each level except the last level. And the number of activation records pushed is h minus 2 because the last function instance is the base case of recursion. So the maximum size of the runtime stack is h minus 2 or OH. Height of a PBT of n nodes is log of n plus 1 and height of an ACBT of n nodes is O log n. A single function instance takes O1 space because it uses only two variables. So space is O log n, size of the runtime stack. Tree traversal. The tree is a non-linear data structure. It requires an algorithm to ensure traversal, that is, visiting every node exactly once. We concentrate on traversal algorithms for binary trees only. The first class of traversal algorithms is called depth-first traversal, in which we focus on moving from the top to the bottom. There are three algorithms of this kind: in-order traversal, pre-order traversal, and post-order traversal. In-order traversal. Start at the root. When standing at a node, 1. Move to the left subtree. 2. Visit the node. 3. Move to the right subtree. We print the data field of a node when we visit it. The node is visited in between the left and the right child, and the acronym for in-order traversal that I use with my students is LNR, left node right. So look at this tree. I am going to conduct an in-order traversal of this tree. I start at the root, which is A. Does it have a left subtree? Yes. Move to it. I come to B. Does it have a left subtree? Yes. Move to it. I come to D. Does it have a left subtree? No. Go to step 2. Visit the node. So I print D. Does it have a right subtree? No. Now everything that we were supposed to do for the node D is done. Go back to node B. You have just visited the left subtree of node B, or you have completed step 1 for node B. So step 2 says visit the node. We print B. Does it have a right subtree? Yes. Move to it. Now we are at E. Does it have a left subtree? Yes. Move to it. We are at H. Does it have a left subtree? No. So step 1 is done. Step 2 says visit the node. So we print H. Does it have a right subtree? No. So we have done all three steps for the node H. Go back to E. We have visited its left subtree. Now we will execute step 2, visit the node. So we print E. Does it have a right subtree? No. All three steps for E are done. Move back. You come to B. All three steps for B are done. Move back. You come to A. You have just visited the whole of the left subtree of A, or you have completed step 1 for A. So now execute step 2. Visit the node. We print A. Does it have a right subtree? Yes. Move to it. We come to C. Does it have a left subtree? Yes. Move to it. We come to F. Does it have a left subtree? No. So step 1 is done for F. Step 2 says visit the node. So we print F. Does it have a right subtree? Yes. Move to it. We come to G. Does it have a left subtree? No. Visit the node, print G. Does it have a right subtree? Yes. Move to it. We are at I. Does it have a left subtree? No. Visit the node, print I. Does it have a right subtree? No. Go back to G. Go back to F. Go back to C. You have just visited the whole of the left subtree of C. Or you have done step 1 for C. Now visit the node. Print C. Does it have a right subtree? No. At the bottom of this slide, you see the traversal sequence that has been created by the in-order traversal algorithm. Pre-order traversal. Start at the root when standing at a node. 1. Visit the node. 2. Move to the left subtree. 3. Move to the right subtree. Again, we print the data field of a node when we visit it. The node is visited before the left and the right child. The acronym that we use for this traversal is NLR, or node left right. Consider this tree. Let's do its pre-order traversal. Start with the root, which is A. Step 1 says visit the node, so we print A and then move to the left subtree. We get to B. Print the node or visit it. Move to the left subtree. We come to D. Visit the node, print D. Move to the left subtree, but there is no left subtree. Now move to the right subtree, but there is no right subtree. We have completed all three steps for D, so we move back and come to B. We have completed 2 steps for B. Now we move to the right subtree of B, which is E. And then we visit the node E, so we print it. Then we move to its left subtree, which is H, and we visit the node H or print it. Then we move to the left subtree of H, but it's not there. Then we move to the right subtree of H, but that is not there too. So we have done everything for H. Move back to E. We have visited the left subtree of E. Move to the right subtree, but there is none. We have done everything for E. Move back. We have done everything for B. Move back. We come to A. We have visited the left subtree of A. We have completed the 2 steps for A. Third step says move to the right subtree, so we move to C. And then we visit this node, so we print C. Then we move to the left subtree, which is F. And we visit this node, so we print F. Is there a left subtree? No. Is there a right subtree of F? Yes. Move to it. We come to G. And then we visit this node, so we print G. Is there a left subtree? No. Is there a right subtree? Yes. So move to it. We come to I and then we visit this node, so we print I. Is there a left subtree? No. Is there a right subtree? No. We have done everything for I, move back. We have done everything for G, move back. We have completed all steps for F, move back. We have completed all steps for C, move back. We have completed all steps for A. The traversal is complete. At the bottom of the slide, you see the traversal sequence generated by pre-order traversal. Post-order traversal. Start at the root when standing at a node. 1. Move to the left subtree. 2. Move to the right subtree. 3. Visit the node. We print the data field of a node when we visit it. The node is visited after the left and the right child, and the acronym that we use here is LRN, left right node. Let us do a post-order traversal of this tree. We start at the root, which is A. Move to the left subtree, I come to B. Move to the left subtree, I come to D. Move to the left subtree, but there is no left subtree. So step 1 is done. Move to the right subtree, but there is no right subtree. Step 2 is done. Step 3 says visit the node. So I print D. Now I have completed all steps for D. I move back to B. I have just visited the left subtree of B. So I have completed step 1. Move to the right subtree. So I come to E. Again I start the 3 steps at E and I execute step 1. Move to the left subtree. I come to H. Now, is there a left subtree of H? No. Is there a right subtree of H? No. The third step says visit the node, so I print H. I have completed all steps for H. I move back to E. I have completed the first step for E. Is there a right subtree of E? No. Then I should visit E. I print E. I have done everything for E. I move back to B. I have completed 2 steps for B. So I should visit B. I print B. I have done everything for B. I move back to A. I have just visited the left subtree of A. Is there a right subtree? Yes. Move to it. I'm at C. Is there a left subtree? Yes. Move to it. I am at F. Is there a left subtree of F? No. Is there a right subtree of F? Yes. Move to it. I am at G. Is there a left subtree of G? No. Is there a right subtree of G? Yes. Move to it. I am at I. Is there a left subtree of I? No. Is there a right subtree of I? No. Visit I. I print I. I have done everything for the node I. I go back to G. I have visited the left subtree of G and the right subtree of G. I visit G now. So I print G. I have done everything for G. I move back to F. I have visited the left and the right subtrees of F. Now I visit F. So I print it. I have done everything for F. So I move back to C. I have just visited the left subtree of C. I move to the right subtree, but there is no right subtree of C. Now I visit C, so I print C. I have done everything for C, so I move back to A. I have visited both subtrees of A. Now I visit A. So A is printed. At the bottom of the slide, you will find the traversal sequence of post-order traversal of this tree. Give traversal sequences generated by all three algorithms for the tree shown here. Have a look at the function traverse_in. This function implements in-order traversal of a tree pointed to by self. If a left child exists, the function calls itself for the left child. So this results in-order traversal of the left subtree. Then we print data of the node pointed to by self. If a right child exists, then the function is called within itself for in-order traversal of the right child. You can see that this is recursive implementation. The function is called for every node. If there are n nodes, the recursion creates n function instances. A single function instance takes O1 time, so the whole recursion takes On time. Let us consider space complexity. The maximum number of activation records are pushed in the longest branch of the tree. If the height of the tree is h, the number of activation records pushed onto the runtime stack is h minus 1. A single function instance takes O1 time, so the space complexity of the whole recursion is OH. Look at these homeworks. 1. Write code for a function of class B tree called traversal that traverses a binary tree using pre-ordered traversal algorithm. The second question is, write code for a function of class B tree called traverspost that traverses a binary tree using post-order traversal algorithm. I'll give you a hint. The codes are very similar to traverse_in. So what did we learn today? We implemented code to determine if a binary tree is almost complete. We were introduced to depth-first tree traversal algorithms. We implemented code for in-order traversal, and we examined all codes for time and space complexities. I want you to read the book, do the homeworks, note your questions, and if you have any suggestions, share them with me via email. Take care of yourself. Allah Hafiz.